So, let us continue the lecture on tangent planes. So, I had done up to this equation. In fact, the measure of d we have computed here, but what was left was the explanation of this underlying property. In fact, we say that a plane is a tangent plane which has the highest order of smallness with an arbitrary point of the surface. So, what actually this means? This means if the distance of the variable point from the tangent plane is d, then what should happen is that limit d upon the distance between p 0 p, when p tends towards p 0 must be 0. Okay. When I say this, that the distance of p from the plane is of highest order of smallness, I actually mean is that the perpendicular distance of an arbitrary point with the plane should go towards 0 faster than the straight line distance p 0 p, okay, when p move towards the point p. So, or I can also say we have a symbol for it, we can equivalently say that d is of the order of p naught p, and p naught p we have just seen is same as under root h square plus k square. So, mathematically speaking, this condition is equivalent to saying that d is of the order of under root h square plus k square. So, here I had started with any plane which passes through the point p 0 whose position vector is r 0, then I will impose on this equation this condition. The minute you impose this condition, your plane will become a tangent plane. Okay. So, now let us continue from equation number 2. So, we are here. So, what I will be doing, I will be computing this. Okay. All right. So, over here in equation 2, for simplicity, if I choose a normal to be a unit normal, then this expression will be simpler. So, if n is a unit vector, that is mod n is 1, then d is nothing but r of u10 plus h u20 plus k minus r of u10 u20 dot n. Okay, this is also 2. So, this is better to deal with. Okay, now, by Taylor's formula, because throughout we are assuming that our surface is regular. So, once the surface is regular, you can expand r 1 u 1 0 plus h u 2 0 plus k by Taylor series. So, by Taylor series, r of u10 plus h u20 plus k is equal to r of u10 u20 okay, plus h times the derivative of r with respect to u1. So, del r upon del u1 at the point p 0 plus k times del r upon del u2 at p 0 plus terms of the order of h square plus k square. So, I have written Taylor series up to first order term. The remainder term is O h square plus k square. Now, we have a notation for these two vectors. So, recall that del r upon del u 1 at point p 0 must be written as r 1 at 0, 0 means p 0, and del r over del u 2 at p 0 will be denoted by the symbol r 2 0. Now, I can take this term in the left side. So, I can rewrite the above expression as u 2 0 plus k minus r of u 1 0 u 2 0, and the right side is h times r 1 at 0 plus k times r 2 at 0 plus terms of the order of square root of h square plus k square. Now, you take dot product with n in both sides, n being a unit normal vector. So, I consider the dot product with n in both sides. So, you can write down one more line. Taking dot product with a unit normal n will give me here also dot product with n. So, I can rewrite dot product with n plus k times r to 0 dot n plus terms of the order of h square plus k square under root. Now, if you look at the left side, this is nothing but the distance d. In fact, since it is not d, in fact, modulus of this will be modulus of this. This is important. Now, modulus, in fact, we want to take it positive. So, this is modulus. Okay, so, d is the modulus of this. So, the left side is d and this is the right side, if now equal to the same thing. Now, if you want your plane to be a tangent plane, then this d must be equal to order of h square plus k square, and therefore, both these terms number 1 and number 2 should separately be equal to 0. This I have explained to you earlier. Somebody may think that the sum of these two must be 0. In fact, both the terms should separately be equal to 0. This I have already explained to you in my earlier lectures. So, if plane 1 is a tangent plane, if plane 1 is the tangent plane, at p 0 we must have d equal to order of h square plus k square, and this is equivalent to saying therefore, plane 1 to be a tangent plane, we must have h times r 1 0 dot n equal to 0 as well as k times r 2 0 dot n equal to 0. Okay. And h and k being not 0, the dot product must be 0, r 1 n is 0 and at the same time r 2 dot n equal to 0. And this tells you that n is equal to r 1 at 0 cross r 2 at 0, and since it is a unit vector, so modulus of r 1 0 cross r 2 0. So, we have determined the unit normal n of the tangent plane. If the unit normal of the plane is the cross product of the basic tangent vector, then this plane will be the tangent plane. So, that is the conclusion that we have. Hence, the equation of the tangent plane becomes hence the equation of tangent plane to the surface R of R u1 u2 at P0, which is in fact R of u1 0 u2 0, which I will be denoting by the symbol R0. Hence, the equation of the tangent plane to the surface at P0 becomes this is equation 1. So, equation 1 will take the form R minus R0 dot n, and n will be R1 cross R2 at 0. Equal to 0, because the right side is 0. So, I am not mentioning the modulus of R1 cross R2. So, this is the equation of the tangent plane, or more simply you can also write down, since it is a scalar triple product, R minus R0, R1 0, R2 0 equal to 0. So, this becomes the equation of the tangent plane to the given surface at a given point. This is the vector equation, and now you can convert into Cartesian form also. If you are given the coordinates of the point in Cartesian coordinate, you can convert it into Cartesian form also. That is easy for us. Let me write down the Cartesian coordinates. So, if r equal to r of uv has u1 u2 you are writing. So, u1 u2 is written as x coordinate is x u1 u2, y coordinate is also a function of u1 u2, and z coordinate is also function of u1 u2. Suppose the variable vector of the plane is capital R. If the variable if the variable vector on the plane is R, which is x comma y comma z, this plane I mean the tangent plane. So, on the plane which is in fact tangent plane. Then the box equation, then the equation of the tangent plane, equation of the tangent plane can be written as scalar triple product is a determinant of these three vectors. So, that becomes x minus r 0 means x 0, y 0, z 0. So, this first component is x 0, okay. Y minus y 0, z minus z 0, and then r 1 0. So, this will be x 1 0, 0, z 1 0. Then you have x 2 0, y 2 0, z 2 0 equal to 0. This becomes the equation of the tangent plane in Cartesian coordinates. This is the equation of the tangent plane. In Cartesian coordinate. And this is the equation in vector form. So, both of them are available to you. If you are given equation of the surface in Cartesian coordinate, this is the equation that you will be using. Otherwise, you can use the vector form also. So, should I discuss some examples also, or how much time? In the implicit form, then what will be the form of the equation for a tangent plane? This is also interesting. If the equation of a surface is in implicit form, namely f x y z equal to 0, then once again we can work out its equation. Since it represents, I am assuming that there is a surface which is represented by this equation, means one of the partial derivative of f is non-zero. So, since it represents a surface, so I can assume that f z is non-zero. You can assume whether f y is non-zero, f x are non-zero, but computation will be same. So, since I am assuming f z equal to 0, the above equation, if you call it number 1, then 1 takes the form, then 1 can be converted into the form z equal to some other function f of two variable x and y. So, the important thing to be noted down over here is then both 1 and 2 represent the same surface. As 1 and 2 represent the same surface, their differentials will give me the same object. Okay? So, as 1 and 2 represent the same surface, their differentials will give the same object, Okay. So, let me differentiate 1 and 2. So, differentiating 1 will give me df equal to 0. So, there is, since f is 0, df will be 0, and df is f x into dx plus f y into dy plus f z into dz equal to 0. The left side is d capital F, and differentiation of 2 will give you df equal to dz. Okay, df is what? Del f upon del x into dx, del f upon del x or del z upon del x, same thing. So, I can write down del z upon del x into dx plus del z upon del y into dy, and equal to dz, yeah, minus dz equal to 0. So, minus dz equal to 0. Okay, these are relation number 3 and 4. As I told you that 3 and 4 represent the same thing, so I can compare the coefficients. Okay, the ratio of the coefficient must remain the same. If two equations represent the same object, the coefficient should have the same ratio. So, I must have del z upon del x upon f x, this must be same as del z upon del y upon f y equal to minus 1 upon f z. Here the coefficient is minus 1. So, on simplification this will give you what? Del z upon del x equal to minus times f x upon f z, and del z upon del y equal to minus times f y upon f z. Okay, these relations I will be calling as relations 5. Okay. Now, you want to work out things in parametric form. So, we had done it in our earlier lecture that R 1 over here is 1 0 f x or del z upon del x, del z upon del x, and R 2 is, we know this from the earlier discussion, we know this fact, and R 2 is 0 1 del z upon del y, and therefore, the cross product of R 1 and R 2 will become minus del z upon del x minus del z upon del y, and this will be just 1. Okay. And from here we had concluded that this is always non-zero vector, and therefore, the representation 1, 2 as well as parametric form are regular. Okay. Now, if you want to work with f x y z equal to 0, so I can change them. Del z upon del x is minus f x upon f z. Del z upon del y I can replace by f y upon f z, and this is 1. Okay. And or I can rewrite it as 1 upon f z. If I write outside, this will become f x, f y and f z. Okay. So, this is the vector which is in fact normal. Okay. So, what does it mean? It means that R 1 cross R 2 is a vector which is parallel to f x, f y, f z. Okay. So, the unit normal for this surface 1, this implies the unit normal to the surface 1. When I say surface 1, means surface represented by equation 1 is f x, f y, f z, and into 1 upon under root divided by its magnitude. This will become unit normal. So, I have got hold of the unit normal n of the tangent plane. So, once you get hold of the unit normal to the surface, you can decide what will be the equation. So, the equation of the tangent plane at the point x0, y0, z0. As the equation of the tangent plane, hence the equation of tangent plane to the surface at x0, y0, z0 is what? Is what? Yes, it is r minus r0 dot n equal to 0. This is the form of the equation. So, r minus r0 will be x minus x0, y minus y0, z minus z0. This is this or dot n you have here. So, this is fx, fy, fz upon under root this thing equal to 0. And since you are computing normal at a point, so this normal I will be computing at the point x0, y0, z0. Okay. So, you may mention the 0 over here also. So, this implies x minus x0 into fx0 if you wish, plus y minus y0. You can put 0 here also, so that you understand that the normal is taken at the point x0, y0, z0. Fy0 plus z minus z0 fz0. So, this is the equation for the tangent plane to a surface whose equation is in the implicit form. So, we will discuss problem in our next lecture. I stop at this point.